get started, I'm really happy to introduce Professor Louis Strigari, who is a faculty member at Texas A&M. Louis did his graduate work at Ohio State University, and then he was a postdoc at Irvine, and then he was a postdoc here for several years. He was a Hubble Fellow here, and I had the pleasure to work with him on many interesting topics. Louis has worked on almost every aspect of dark matter with a particular focus on astrophysical probes of dark matter, from direct detection, indirect detection, and all aspects of astrophysics. He's also worked on neutrino physics and other interesting topics. So today he's going to be telling us about really what I think is a really exciting revolution in our understanding of our own galaxy and what our galaxy can teach us, both about lots of aspects of astrophysics, but also potentially about the nature of dark matter. So thank you very much, Louis.
Okay, so I think the mic is on, everybody can hear me. So thanks very much for the invitation. It's good to be here and see lots of friendly faces again. So, so I'm going to be telling you about some new interesting results relating to the measurements of the three-dimensional motions and the positions of stars in our Milky Way galaxy, highlighting in particular the role of the recently launched Gaia observatory as shown here. And what I'm going to particularly focus on is what these observations say about sort of fundamental processes in the universe, the hierarchical formation of the Milky Way galaxy, as well as possibly even the nature of dark matter. And what I hope to impress upon you here at the end of the day is that these observations are pointing towards sort of a new understanding of our galaxy, sort of a new non-equilibrium picture of our galaxy, and that in order to extract information from these observations, we have to really understand and embrace this complexity that these observations are pointing to. Okay, so let's kind of just start from the very beginning. This is a very broad audience here. So, so there's like a little bit of an astronomer in all of us, right? In the sense that with our unaided eye, we can, note the positions and sometimes properties of celestial bodies in the sky. In particular, when we note the positions and motions of such bodies, we're endeavoring in the field of astrometry or positional astronomy. So there's of course an observational aspect of astrometry involving standard instruments, data recording devices to measure the precise positions and motions of stars, planets, and galaxy. There's also a theoretical component to astrometry, which involves the use of dynamics, as well as the establishment and understanding of reference frames in order to understand the motions of these bodies. So now, as our ancient ancestors could have told us, we, with our naked eye, can discern the motions, clearly discern the motions of 7 celestial bodies. These are the so-called wandering stars, right, or planets in some instances. So the image you see here is that of the nearest stellar system. This is actually Alpha Centauri. It's a triple star system. And even though we cannot perceive this with our naked eye, stars such as Alpha Centauri do in fact move. Okay, so how do we know how far away the stars are from us? Well, as we teach our Astronomy 101 students, this is done using the Parallax Method. So, so consider here a foreground star relative to more distant fixed background stars. If we make a measurement of the position of that foreground star relative to the background stars at some point in the Earth's orbit, then do it again 6 months later, the more nearby star will shift relative to the distant background stars. The angle by which this foreground star shifts by is called the relative parallax angle. Okay, so for the nearest stars to our sun, this parallax angle is somewhere in the range typically of approximately 0.1 arc seconds, corresponding to distances of about, say, tens of light years or so. Okay, so the first actual parallax that was measured was done by Bessel in 1938, where he measured the parallax angle of the star system 61 Cygni, and he measured this parallax angle to be about 300 milliarc seconds, corresponding to a distance of about 10 light years or so. So this is actually one of the nearest stellar systems to our sun, and since 1938, as you can see, has had its parallax measurement revisited many times. Okay, so parallax tells us how far the stars are away from us. How do we know how fast the stars move? Well, of course, to know how fast the star is moving towards or away from us, astronomers use the Doppler shifting technique by looking at the Doppler shifts of spectral lines of stars. Okay, so to measure the transverse motion of a star or the proper motion of the star requires a precise measurement of the position of that star at some epoch and then a precise measurement at some other epoch. Okay, and so typical times between these measurements can be anywhere from, say, a few years to tens of years. All right, so dividing the change in position by the change in time, and the measurement gives us a measurement of the proper motion. Okay, so typical proper motions for nearby stars are anywhere in the range of about 0.1 arc seconds per year. So the star with the largest proper motion in the sky is called Barnard's star. This is a low mass dwarf star which has a very large proper motion of about 10 arc seconds per year. Okay, so what science has traditionally been done with these astrometric measurements? Well, for one, it actually provides an interesting way to study binary star systems. So here you see the orbit of two stars in the star system 61 Hercules, about their common center of mass here in the upper left. The bigger diagram here shows the motion of the center of mass of 61 Hercules, and it shows the motion of the components of that system about this center of mass. And for one of those components, you can also see the parallax motion associated with it. So this is here, it's an example of an astrometric binary system. Okay, it provides astronomers a unique way to measure binary star systems in the universe. And the interesting aspect of this is you can actually measure that there's a binary star system associated with this stellar system, even though you actually can maybe only discern one of the stars from photometric measurements. Okay, so since the earliest astrometric measurements have been done, we actually have learned a lot about the structure of our Milky Way galaxy and the sun's place within it. So in particular, combining these astrometric measurements with more traditional photometric astronomy techniques, we have learned that the sun is at an approximate distance of about 8 kiloparsecs from the center of our Milky Way galaxy, residing in the minor Orion spiral arm. So the sun is approximately 20 parsecs above the plane of the galaxy. So at the position of the sun, a particle moves with a circular velocity of about 220 kilometers per second around the center of the galaxy. And the sun actually moves approximately 20 kilometers per second with respect to this local standard of rest velocity of 220 kilometers per second, and it moves towards a direction of positive galactic latitudes and longitudes. Okay, so this information was obtained by looking at the motions of nearby stars relative to the sun. Okay, so let's look a little bit more about the motions of these nearby stars. Okay, so here's a distribution of the velocities of a group of a particular type of star near the sun, okay, in 3 coordinate directions, where the coordinate system is indicated there in the upper right. Okay, so the interesting aspect of this is in each of these coordinate directions, the velocity distributions are different for this group of stars. Okay, so so we can see that the velocity distributions not only depend on the coordinate direction, they've also been found to depend upon the type of star. So for example, you have different distributions for old stars than you have young stars. Okay, so this concept here goes back to the 1950s when astronomers first recognized it, goes by the name of Parnengo's discontinuity. Okay, so with the measurements of the components of these velocities in these 3 directions, one can also construct what's called the velocity ellipsoid. Okay, so then if you find that the ellipsoid, the principal axis of this tensor, which you construct from these ellipsoid measurements, aligns with the symmetry axis of the galaxy, then you can actually prove that the local stars are in a state of dynamical equilibrium. And similarly, if it does not align, then that is a hint at non-equilibrium dynamics, or say axisymmetric structures in the galaxy, such as a bar in the galaxy, or perturbations due to spiral arms. Okay, so all the measurements I've been talking to this point can be done really with ground or earth-based astrometric measurements. Okay, so there's a benefit to doing astrometry from space, and a few of the main benefits are listed here. Of course, when you're up in space, you avoid the atmosphere and refraction and turbulence from it. So you have torques that modify the positions of the image if you have an instrument on the ground. Very importantly, you can actually observe the entire sky with a single instrument if you can do astrometry from space. And this is actually really important because it actually allows you to measure what's called the absolute parallax angle of a star. And this essentially is the parallax angle of a star that is different than the relative parallax, which I described earlier. So essentially the angular shift of the background star actually cancels out. So this is actually, this is a big benefit to doing astrometry from space. So the first space-based dedicated astrometric mission was the Hipparchus satellite, which launched in 1989 and lasted approximately 4 years. So Hipparchus operated on a highly elliptical orbit. So went as far out as about 3,600 kilometers, as close in as about 500 kilometers. Hipparchus is a drift scanning instrument basically that scans the sky in great circles and positioned stars along little segments of those great circles. So it simultaneously observed two fields separated by a wide angle about 58 degrees, and this wide angle was important to obtain these absolute parallax measurements that I described earlier. Okay, so here's an example of a trajectory of a given star that Hipparchus observed. So here, those little segments you see are the segments of the great circle along which Hipparchus would align a given star. And you see a trajectory of this particular star, which is a combination of its proper motion and its parallax motion. And so basically by solving a large set of equations, Hipparchus could reconstruct the trajectory of approximately 100,000 stars that are nearby to the sun. And in doing this reconstruction here, Hipparchus actually ushered in the era of milli-arc-second astrometry. So dating back to 100 BC, the precision of astrometric measurements by actually Hipparchus himself was approximately 1,000 arc seconds. And so now we've all the way down to sort of the modern day and age, where we have where we're measuring parallax angles to sort of milli-arc-second accuracy. Okay, so Hipparchus produced many important scientific results in a very interesting catalog that people really to this day have been doing science with. So Hipparchus measured for approximately 100,000 of the nearest stars. It measured their distances to an uncertainty of approximately 20%. So it made important contributions to several fields of astronomy, including stellar structure and evolution, learning about the properties of stars as indicated here. I mentioned earlier some stuff about galaxy kinematics and dynamics, how does the sun move relative to nearby stars. It also made some important contributions to solar system astronomy. And very importantly, it also provided the first optical length. It measured the positions of these stars so precisely. It provided the first optical length to an extragalactic reference frame, which was defined by radio interferometric measurements of quasars. And it determined that this reference frame didn't rotate with respect to these quasars up to some uncertainty of about 0.1 milli-arc seconds per year. Okay, so this leads us here to the era of modern space-based astrometry. So in this day and age, we do astrometry primarily in space through these two instruments here. One is the Hubble Space Telescope, and the other is the Gaia experiment. So the Hubble Space Telescope, of course, was launched more or less around the same time Hipparchus was, and actually has two instruments which is able to do astrometry with fine guidance sensors and the wide field cameras. So HST does a differential astrometry in the sense that it just measures it makes astrometric measurements of objects with respect to sort of background stars or quasars in its field. On the bright side, it has a well-concentrated point spread function, which means that HST can actually measure very faint stars, but a technical point is that in some cases this point spread function can be undersampled, which means if you're trying to get sort of sub-milli-arc-second precision, it can have difficulty sort of positioning the center of the star within a given pixel. Okay, so Gaia is the direct successor to the Hipparchus satellite, which I described earlier. So Gaia was launched in 2013. It is now parked at the L2 Lagrange point. So Gaia, like Hipparchus, does large angle global absolute observations from space, so it's able to measure absolute parallaxes for a large sample of stars. So it positions stars on CCD pixels, which is actually different than the way that Hipparchus did it, because Hipparchus was launched in the early 1990s. And the field of view between the two fields that Gaia observed is approximately twice that of Hipparchus, about 106 degrees. Once again, this wide angle astrometry is useful for these absolute parallaxes. Okay, so Gaia's reach here. So here's a schematic from their website about what they can do relative to Hipparchus. So that little dot there you see in the middle are the sort of 100-ish parsecs around the sun, which Hipparchus is able to make distance measurements of 10–20% uncertainty. And by the end of Gaia's mission, it's going to extend to make precise measurements of stars at that level for stars out to the galactic center and beyond, say some 10 kiloparsecs from the center of our Milky Way galaxy. Okay, so it measures the parallaxes, proper motions, and positions of ultimately about 1 billion stars in the Milky Way galaxy by the end of its mission. In addition to doing this, it actually also measures the radial velocities, or the line-of-sight velocities, for the brightest 7 million stars in its catalog. And this is something that Hipparchus did not directly do. And this is actually particularly interesting because, say, for these bright 7 million stars, it gives you all 6 phase space coordinates of the star, 3 components of its velocity, and the 3 components of its position you have. Okay, so you can do really some interesting dynamics from that perspective. So here's going back to our schematic figure from where we started with Hipparchus himself down to Gaia. Now we're clearly going down to the area here of sub-milli-arcsecond astrometry relative to Hipparchus. In some cases, say for the brightest stars, a couple orders of magnitude or more precision in terms of the positions in the parallaxes. Okay, so here's kind of one of the more iconic images that have recently come out of the Gaia satellite. This is a view, an optical view of our Milky Way galaxy as viewed by Gaia. This is a picture of over 1 billion stars in the galaxy, showing sort of a density pattern that you see when you bin all the stars together. Of course, the most prominent feature in our galaxy is the galactic disk. Okay, it's an optical, so lots of regions are obscured by dust, as you can see. So this is a picture about, like I said, 1 billion plus stars. It's already made tremendous contributions to many areas of stellar astrophysics, galactic dynamics. So what I'm going to do for the purposes of this talk is try to go and connect this to sort of these processes which I described earlier. So for example, how did the Milky Way galaxy form? You know, what do these observations, if anything, tell us about the nature of the underlying dark matter in our Milky Way galaxy? Okay, so these are the particular topics that I'll cover during the course of this talk. So I'm going to talk a little bit about the recent measurements of the phase space structure of the Milky Way disk using the Gaia satellite. Some local luminous, understanding of the local luminous and dark matter distributions from these measurements, as well as identification of stellar streams. And then I'll talk about a particular topic that I've been involved in the past several years, understanding the nature of dwarf galaxies and dark matter subhalos, what are called dark matter subhalos in the Milky Way, and trying to figure out what Gaia would tell us about those entities. Okay, so that was a picture that I showed earlier that we see, right? You know, we see optical photons coming at us. So if you actually had dark matter eyes, or you lived in sort of dark matter theory land, this is a picture you would see. So this picture here comes from one of the highest resolution dark matter simulations of the distribution of matter around a galaxy like our Milky Way. So in that little dot there in the very center, so that's where all of the stars in the Milky Way disk that we know of would reside. Okay, this is essentially a density map of the dark matter distribution around the regime of our galaxy. And the first thing you will note here is, of course, this distribution is in fact not smooth, okay, but it's very lumpy. So something like anywhere from up to 10 to 50% of our Milky Way galaxy, the mass of it can be contained in these dark matter lumps. These are typically called subhalos or dark matter substructures. Okay, so this is one of the most interesting predictions that have come out of these simulations in the past 20 or 30 years about the underlying dark matter distribution in our galaxy. So in addition to this prediction, sort of a lumpy distribution around our galaxy, it's also been noted that if you look at an individual dark matter subhalo, right, which is an object within which visible stars reside, if you just measure sort of the density distribution of a given subhalo, that density distribution more or less has a universal shape to it. Okay, and very importantly, it's actually independent of the mass of the dark matter object itself. Okay, so anywhere from the largest cluster of galaxies down to the faintest dwarf galaxies we know have more or less the same dark matter density distribution, and this goes by sort of the famous Navarro, Frank, and White model, named after the authors who first brought it to prominence in the 1990s. Okay, so these are kind of the two key predictions of our sort of standard cold dark matter model at this stage, right? Lots of substructure, lots of sort of debris in our Milky Way galaxy that's come from disrupting substructures, okay? And also sort of this universal density profile shape that is predicted in these simulations. So these are the ideas here that we're going to test here for the next half an hour or so for this talk and see what the Gaia observations can say about them. Okay, so let's kind of start very local and then go outwards a little bit in the halo. Okay, so here is a cartoon not drawn to scale of our Milky Way disk, sort of plopped on one of those simulations, the position of our sun in that disk. Okay, and these figures here show measurements of the velocities that have been recently published by analysis of Gaia data So this is the radial velocity versus the z component of the velocity, and also the radial velocity versus the azimuthal component of the velocity, sort of just scaled to a characteristic velocity in the halo. Okay, you see a bunch of dots on these figures, right? These are all sort of particles that have come from different dark matter subhalos, right, that have been tidally stripped, right? And now these sort of dark matter particles that are sort of tidal debris from these galaxies now reside in sort of this local solar neighborhood to the best resolution that these simulations are able to obtain. So, so the prediction, even going back when these simulations first started, was that there should be anywhere from sort of like, a few hundred or so sort of faint streams sort of in the local solar neighborhood that come from sort of tidally disrupting debris that is left over from these objects. And as I mentioned, the color scheme there, each of those colors, if you can make them out, actually comes from a different progenitor subhalo. So this is a prediction itself of the underlying model. Okay, so now let's look at what actually Gaia says about the stars in the solar neighborhood. Okay, so sort of zooming in a little more on the structure of our Milky Way galaxy, one can break our Milky Way galaxy up in sort of the two types of disks, if you will. There's a thin disk, which is older in terms of its population of stars. It's less metallicities, less iron component to those stars in that disk. And there's a thinner disk, which is younger populations of stars, which have formed more recently. Okay, so those two disks are indicated in the figure there. So one of the first things that was done, you take the Gaia data, basically measure the velocity dispersions of the stars in the local solar neighborhood, and you can actually once again determine that for stars in the thick disk and for stars in the thin disk, the velocity dispersions are different. So this goes back to this Parnengo's idea that for different populations, you see different velocity structure of the stars. So in particular, the velocity dispersion of the thin disk stars is less than the velocity dispersion of the thick disk stars. And the idea here is that the thick disk stars have been around for longer and they've had more time sort of to have random interactions, say in the galaxy to sort of inflate their velocity dispersion. So this is sort of a consistent picture which is now developed here through many observations, and this is what the preliminary results from Gaia also indicate. Okay, so what about this ellipsoid measurement, which I said earlier tells you about, is there some non-axisymmetric structures in the galaxy, or, is there non-equilibrium dynamics going on? Okay, so, well, using these initial Gaia measurements for both these sample of thin and thick disk stars, one can actually make a measurement of this ellipsoid perpendicular to and in the galactic plane. Okay, so in particular for the top one, within the galactic plane, it's found that there is actually a tilt angle relative to the symmetry axis of the galaxy. So this tells us that for some of these populations, say for some of these metallicities, right, there might be signs of non-equilibrium structure in the dynamics of the galaxy. So this actually only occurs sort of when you bin the stars up into different sort of categories in terms of their metallicities. Sort of if you globally average all the stars, one can show that this tilt angle basically goes away. So sort of from a global perspective, you might say that the system is in dynamical equilibrium, but individual components of it are not. Okay. All right, so let's kind of take this up a notch here and I'll show a series of more famous figures that have come out very recently from Gaia. So here's the velocity structure of stars in the plane of our Milky Way galaxy. Okay, so U and V are velocities in the plane of the galaxy. So each of these points here are stars, and all these stars are sort of within a region of about 200 parsecs from the sun, so very locally in the solar neighborhood. And very interestingly, here you can see sort of faint arches, right, or sort of cluster-like structures in this projection of phase space. And sort of these sort of arch-like structures, sort of if you follow along the top, you can actually see this. And this is the first time these structures have actually ever been seen. So previous Hipparchus measurements were not able to resolve these type of structures in the galaxy. So there's sort of low-density arches throughout, as you can see. There's a famous stream here located at velocity there on the y-axis of about -40. So that's the Hercules stream. And if you squint very, very hard, you might be able to see that it's possible that this Hercules stream is sort of bifurcating. Right? This is the first time that this has actually been identified. There's these phase space clumps here that may be associated with known star clusters. The Pleiades is actually a famous local star cluster that may project into this component of the velocity space. The Hyades star cluster is actually a star cluster that's been measured by many astronomers through the decades, and you can actually see a possible velocity structure associated with the Hyades itself. So this is an entirely new way now to look at what's going on in the phase space structure of the Milky Way disk. Okay, so here's actually a very famous figure that came out recently from the Gaia Observatory. Once again, looking at velocity and spatial projections of stars in the galaxy. So for example, this shows the z components of the velocity and the z components of the position. So z components basically up and out, up and down from the galactic plane. So if you do a projection, and on the left there you see a binning based upon density, right? So, and if you can maybe very faintly sort of make out sort of this spiral that you see gets more dense sort of as you go towards the edges of the spiral. So this is a phenomenon here known as phase mixing, which ultimately indicates this might actually be a very recent structure in the galactic disk. It's much more spectacular when you view this projection on the right. So the z component of the position and the z component of the velocity, and then you bin based upon the azimuthal velocity, you see this very neat spiral-like structure in this projection. And this actually could be an indication that the z component of the velocity and the phi component of the velocity in this case are coupled. So once again, this could be a very recent structure that formed, and the thought is that this could have been formed from a possible impact of one of these dark matter subhalos in the outer edges of the disk, which then sort of set this oscillatory behavior in motion. Okay, so is this sort of direct evidence that we see in the Gaia data for an impact of one of these dark matter subhalos in the localish solar neighborhood? Well, it turns out sometimes the interpretation, the interpretation might actually not be that clean. Okay, and to think about why that might not be true, you want to look at different projections of this data. Okay, so on the left column there, you see sort of projections in velocity space, as well as projection in what's called action angle space of the distribution of stars for a purely axisymmetric system. Okay, so it benefits to go into action angle space to look at these variables because in that sense you can actually assign these physical quantities here that I've plotted to individual orbits, so you can actually more physically track individual orbits of stars in the galaxy. So the left there is a projection for a purely axisymmetric system. The right there is actually what we see in the Gaia data. So you'll recognize the upper right figure from the previous slide, sort of that structure in velocity space. There's also, once again, the structure in this action angle space as well. And sort of the structure has the shape that it does basically because you're seeing stars sort of down there at the bottom of that V, if you will, sort of are confined within the galactic disk, whereas stars sort of in that upper region of the plane, sort of they come in the galactic disk, but they come in sort of very, very eccentric orbits. Okay, and so the idea is maybe if you look in different projections of this phase space, you can kind of discern between a solution whether a dark matter subhalo came in and set this oscillatory pattern in motion, or there was some other physical effect going on. So what is that other possible physical effect? So two other ideas that have been noted is that these could just be dispersing open star clusters that have formed. So this, the sun formed as part of an open star cluster, which is now dispersing as the system sort of, evolving in the galaxy. And we could be seeing that type of structure happening in velocity space and in this action angle space. As I mentioned, the solution that there was a possible accretion and disruption of a satellite. Okay, so that would be associated with an accretion of one of these dark matter subhalos. A very plausible interaction, which has been discussed by some theorists recently as well, is sort of resonant interactions with these non-axisymmetric features in the galactic disk. And the idea here is that if you look at, once again, in these projections in this action angle space, you can actually find that these resonant interactions would occur at specific values of the angular momentum. So this is actually still a very open question, and no one really knows what the nature of this phase space structure in the disk is, but this is certainly an avenue of intense research here going on really up to the moment here. Okay, so what does this actually say about local dark matter properties, and what can we say about local dark matter properties from this Gaia data? So another interesting point that's been noted in the data is sort of if you look at stars that don't say belong to the galactic disk, but belong to this more like extended halo of stars in the galaxy. So sort of around the disk, there's stars that are kind of floating around. Those are part of the stellar halo. And if you identify a population of stars that belongs to that stellar halo, right, and measure their velocity distribution, you actually find something very interesting. You find sort of an older metal poor component that has more or less isotropic random velocity distribution, and you find a newer component, a more metal-rich component that has more elongated structures in velocity space. Okay, and so the idea is that that component that's more metal-rich with those elongated orbits may have actually resulted from a recent merger of one of these dark matter subhalos, say something like 10 to the 10 times the mass of the sun, and there's a cartoon of such a merger possibly occurring, and this would be once again a signature of these subhalo interactions that are predicted in the cold dark matter cosmological model. Okay, so these are stars that we see, of course. So there is believed to be associated dark matter particles with those galaxies that have come in along with those stars, and there's been some recent work done trying to understand how do we predict the local velocity distribution of dark matter if such a collision occurred in our galaxy in the relatively recent past. And the idea here is that there would be then sort of these sort of streams of dark matter particles, if you will, and that you'd have deviations from the velocity structure that's typically assumed for those who analyze direct dark matter detection experiments. So the issue now is it's not really clear how much dark matter do we associate to that type of interaction at this stage, and this is really still a bit model dependent, how much dark matter sort of comes in with the stellar distributions. Also, another interesting point is recently one can look at the local stellar distribution from the Gaia data and determine, is there a disk of dark matter associated with the Milky Way galaxy. This has actually been a subject that's been talked about for the past several decades in astrophysics. And the idea here is that you would have one of these satellites get accreted into the Milky Way galaxy and sort of say it gets accreted sort of along the direction of the galactic disk, and then ultimately mixes in with the disk and forms a disk of dark matter. So according to, there's been no observational evidence for such a disk yet at this stage. This is just sort of a figment in the mind of theorists. One can actually look at the Gaia data, and that was actually done recently. Sort of variations of these calculations have been done going back to Oort and Bacall to look for such a structure. And yet in the Gaia data, there's actually no evidence for such a disk up to the precision which they make the measurements. Okay, so this was local measurements. So let's take a step back here for the next 15 minutes or so. Let me talk about, like I said, a subject that I've thought about quite a bit recently, and that's understanding sort of bound substructures in the Milky Way galaxy, or what astronomers call dwarf satellite galaxies. So you saw all those lumps in that image of the simulation of the cold dark matter cosmological model, and we believe, according to the model, that some of those lumps have stars associated with them. Okay, and if they do, we call those dwarf satellite galaxies of the Milky Way. So from an observational perspective, this is our current understanding of the known population of dwarf satellite galaxies. So this is a projection in galactic coordinates where the galactic center is in the center once again. And you can see we've got a lot of dwarf satellite galaxies that we just recently discovered in the northern galactic cap, thanks largely to the Sloan Digital Sky Survey. And we've got many new dwarf galaxies that have just very recently been discovered, thanks in large part to the Dark Energy Survey. A lot of that work has been done here to find these new objects. So now we're up to something like 40 dwarf satellite galaxies. The interesting aspect of these systems is these are basically the faintest known galaxies in the universe, right? In some instances, containing only a few hundred to 1,000 times the luminosity of the sun. They all appear to be incredibly dark matter dominated. They have in some instances something like hundreds times more dark matter mass than they have stellar mass. So they're not only the faintest systems known in the universe, they're the most dark matter dominated systems known in the universe. Okay, and the question I'm going to ask going forward here is what can Gaia actually say about these systems? Can they actually go in and understand the internal kinematics of these objects? And then can we actually determine whether we have something like this Navarro-Franken-White density profile that's predicted in cold dark matter? Okay, so let's talk about that for a little bit. So let's go into a little bit more details about these dwarf satellite galaxies. So this is actually an observational and theoretical subject that's kind of taken off in the past 10 or so years with some recent high-resolution spectroscopic measurements of of many of these objects. So here's a classic figure from 2007 which shows the velocity dispersion versus the radius for many of these systems. And an example system there is a Sculptor Dwarfs toroidal galaxy, which you have to kind of really, really squint to make out the stars that form the galaxy relative to the background stars. It's a sort of very diffuse structure. So the thing you'll note here, of course, is that the velocity dispersions of these systems are more or less constant. They're something in the neighborhood of 5 to 10 kilometers per second, depending upon precisely the system that you measure. The reason we know that they're very dark matter dominated is because you look at those solutions there with the solid line, that includes a dark matter halo component in these systems, whereas the dashed line here in all cases says the gravitational mass just comes from the stars. And as you can see, that solution fails in all circumstances, and it more or less fails in every single system that we know about. So the idea here is from a theoretical perspective, when what I'm interested in is, like, do these systems have dark matter, these central dark matter cusps that are predicted by Navarro, Frank, and White, or do they have constant density structure cores in them, which might be a signature of deviations from the standard cold dark matter cosmological model. There's been lots of dynamical analysis that's been thrown at these systems over the past 10 years. I've got some references here. Sort of the simplest thing to do is assume that these systems are spherically symmetric. They're isotropic in their orbits. They're in equilibrium. They're not being tidally disrupted by the Milky Way. There's actually good theoretical motivation for that, which I'll show shortly. One can also do more complicated dynamical models than what I just mentioned. You can add non-spherical models to this, to the theory, to how to understand these systems, more self-consistent stellar dynamical models. Kind of just a point I want to get across through the slide is no matter how you do this analysis theoretically, they all more or less agree on, well, they might not agree sort of what's the exact structure of this dark matter density distribution, say in the center of the galaxy. They more or less all agree that there's an integrated dark matter mass, say within the stellar distribution that you see, and that thing is actually measured very precisely, independently of how you do the theory, or what the system is. Okay, so the interesting thing about these systems is they're very, quote unquote simple, right, for astronomical systems, right? They're just stars orbiting, gravitational potential dictated by the dark matter distribution. And so that was one of the reasons why these systems became incredibly interesting and important for the context of dark matter. But as these things go, the more you learn, the more complicated they get. Okay, so here's an example here of this Sculptor Dwarfs toroidal that I showed you. And this has actually become an object of particular interest because it's actually not so simple in the sense that it has sort of two populations, if you will, of stars. It has a sort of a high metallicity component shown by the red distribution in that figure, where you're just looking at a projected density distribution of stars in the galaxy. And the blue there shows an older, more metal poor distribution of stars. And the interesting thing is that these two distributions not only are sort of different spatially, right, they're different in velocity space as well. So similar features to we saw sort of in the local Milky Way disk that Gaia had helped identify as well. Okay, so this is one of the first evidence of multiple stellar populations in a dwarf toroidal galaxy. And this is actually, is really interesting, not in the sense of understanding that, but also from a kinematic perspective, because essentially it gives you like two data points, right, to try to measure the dark matter density distribution. You can use, population A of stars and then population B of stars, and then try to use those measurements to get the density run of the dark matter in this object. Okay, so there's been lots of literature on this analysis, and very recently it was actually indicated that sort of this multiple population measurement, sort of when you do the sort of very basic analysis, actually rules out this Navarro-Frank-White cold dark matter cosmological model. Okay, in the sense that it measures something that does not look like it at high statistical significance. So some work that I've done here is more, the more complicated you make the theory, if you will, or the more you bring into the theory, the more sort of free parameters you bring in, and sort of now it's really at some level understood that these observations, sort of what you get in terms of the dark matter density distribution, depends sort of how you do the theoretical analysis, which is really sort of unsatisfactory at this point, but that's kind of just like where we are at the data, with the data. Okay, but there's one more thing we could do with this. We could try to use astrometry, right? So I actually didn't personally think this would be possible with something like the Gaia Observatory, okay? But some very creative astronomers very recently took measurements of the positions of about 12 stars in the Sculptor Dwarfs toroidal galaxy using the Gaia data. and combined it with data from the Hubble Space Telescope about 20 years earlier to measure the proper motions of these 12 stars that are inside the dwarf galaxy itself. So this actually is very interesting in the sense that it not only gives us the velocity of stars towards away from us from this Doppler shifting method, but for the very first time, these astronomers were able to resolve the projected velocity dispersions intrinsically of stars in the Sculptor Dwarf galaxy. So they measured these precisions to about 3 to 4 kilometers per second. And each one of those components there is a different component, say, you can think about in the plane of the sky. Okay, so this is very interesting because there's been theoretical noise in the past 10 or so years that if we had this information, we could actually possibly break this degeneracy and actually learn something about the nature of the dark matter core cusp in these systems, and therefore is the dark matter, say something like the cold dark matter model that we believe in. I should also mention that, there's some detailed bullets there. It was believed that one could do these types of measurements just with HST alone. That actually turns out at the moment to be very hard. There's some ongoing work to try to do that, but it's not very easy, and it's a very very difficult data analysis problem at this stage. Okay, so we got really excited when we saw these first ever intrinsic proper motions of stars in a dwarf galaxy in the case of Sculptor. So we immediately tried to analyze these systems and say, okay, are we at the stage now where these astrometric measurements can tell us something about a core cusp in this halo? And to make kind of a long story short here, the answer, unfortunately, is no. So bottom right there gives you sort of those measurements of the radial velocity of stars in Sculptor, which I showed earlier. The top two panels give you these astrometric velocity dispersions. Okay, and as you can see, those errors are still relatively large compared to the line of sight velocity. So you can kind of manifestly see this with your eye, why this actually doesn't work. Those bands there, if you can make them out, say the blue one is for, say, a non-NFW model, which has a constant central density of dark matter, and the red ones are for the NFW model. So we got to try to distinguish between those things, for example, if we want this thing to work. So what we discerned here is that might require proper motion velocity dispersion uncertainties of something like 1 kilometer per second, which is about what we have now with the radial velocities of the stars. This is not possible with current Gaia data, but maybe as I'll mention towards the end, who knows what can happen in the future. All right, there's one more but here, okay? And this is some work that's currently in progress by my postdoc Andrew Pace. So there's a particularly interesting dwarf spheroidal galaxy, Sagittarius. And this is quite spectacular, and if you can make it out here, this is actually getting tidally destroyed by the Milky Way galaxies. Something like 10 to the 8, 10 to the 9 stars, maybe once associated with it. So it's leaving sort of this trailing debris, right, as the object's getting disrupted by the Milky Way disk. And here's an image from David Law, who made who did some simulations of this object evolving in the Milky Way. Okay, so there's a lot of tidal debris associated with this object. There is sort of a central core of stars that you see that should at some level be sort of still remaining in dynamical equilibrium, and there should be some dark matter associated with that object. And so we've been really interested in the central regions of this object recently because this object does have bright enough stars where Gaia actually can resolve the intrinsic proper motions to get the velocity dispersions of these systems. So there's ongoing work right now to try to understand if we can actually make a measurement distinguish between a core and a cusp in these systems. Also, Sagittarius is close enough that you can actually measure sort of the stellar distribution in 3 dimensions. So there's a particular type of star called an Aura Lyrae star, which lends itself to measuring precise distances to individual stars. And by identifying hundreds of those in the Sagittarius dwarf spheroidal, we can actually not only measure the projected distribution of stars, but also the 3-dimensional distribution. So it's possible we could have more or less complete phase space coverage for a large group of stars in the center of the Sagittarius dwarf here. The problem, of course, is the thing is getting tidally disrupted, and there might be some systematics that come in that we don't understand that we need to account for along those lines. But this is exciting work that actually might help us bypass this issue of that the Gaia data aren't yet sensitive enough for a more traditional object like Sculptor. Okay, so what these objects do, so even though we can only resolve the intrinsic dispersions sort of in very special cases, these Gaia measurement combined with HST measurements provide very exquisite orbits of these dwarf galaxies around the Milky Way, sort of, and so it gives us a 3-dimensional orbital trajectory of the system So we can do things like learn about maybe when these systems fell into the Milky Way galaxy, how many passages have they made around the Milky Way galaxy. So here's particular HST observations that come for the Draco Dwarf galaxy and the Sculptor Dwarf galaxy. So just from HST observations alone, we can actually have precisions to about 10 kilometers per second, which is really unprecedented up to this point for the sort of the global proper motions of the orbits of these systems around the galaxy. And I'll kind of get back to in a minute why this is generally interesting in the context of the cold dark matter model. Okay, so speaking of these orbits here, we know, like I said, of approximately 40 or so of these dwarf galaxies in the Milky Way. Combining Gaia with HST basically gives us the coverage to get the orbits of all these systems to precision that's been not done before. And really an interesting point here that goes back to Donald Lyndon Bell, I believe in the 1970s or even earlier, is that if you look at a large fraction of these satellite galaxies, they all appear to be rotating in more or less the same plane around the Milky Way galaxy. So the question is, how did those things form? Did they all kind of come in sort of along one filament as they got accreted into the Milky Way? So here's an example of all the objects within about 50 kiloparsecs of the Milky Way. And those distributions you see are what's called the distributions of orbital poles, right? So basically you define the motion of the orbit of the object around the galaxy. So then the pole there is a vector perpendicular to that. So one is able to discern by looking at these orbital poles that most of these objects live in a plane. And really it's up to the cold dark matter model to try to understand that. Okay, and this is sort of new information that's come along. So we can actually go into the simulations, okay, and identify particular objects in those simulations that we believe resemble, say, a particular dwarf galaxy. Okay, so the simulations have become that good and the observations have actually become that good. So here's an example we did for the Fornax dwarf galaxy by examining systems in these simulations that we believe resemble this object. So here's two tracks that the Fornax dwarf galaxy could have gone on. So there you read from left to right and left to right. Those are two example systems that could be Fornax. And actually this is quite interesting because the one you see in the very left there, that corresponds to today. You can see like a whole bunch of tidal debris coming off that system, and you see just a sort of a centralized core sitting there that corresponds to the object that we see. Okay. Also, you could have another solution where the object, where you could sort of match sort of the kinematic properties of the central object, where you have much less exaggerated tidal debris structure. Okay, and the interesting thing is that we at this stage we actually cannot distinguish between those two solutions for Fornax. So an interesting point is that one could actually go and look into the data itself using a survey like the dark energy survey, and ultimately we're looking at this with Gaia as well, if we can do this kinematically. Look at the structure of the object, and do you see sort of faint tidal debris associated with Fornax? We're now getting these very precise photometric surveys that allow us to do this. So the question is, do we see sort of that sort of central structure there in the red circle on the left? Sort of do we also see elongated tidal features? And the answer is, to the best of our knowledge, according to a recently published analysis we had with the Dark Energy Survey, the answer is no. We don't have any faint tidal debris associated with Fornax. Okay, so at this stage we're not able to determine if it has tidal structure associated with, as might be predicted in some of the cold dark matter models. Okay. Another recent point I want to make about these orbits, and this is a project done by my graduate student Alex Riley. So he actually looked at sort of the statistical properties of the orbits of all the known dwarf satellites around the Milky Way and sort of compared them to what we might expect in cosmological simulations, as I showed earlier. And the interesting idea that he hit on here is that if you look in the very central regions of the Milky Way galaxy, say for numbers, say within about 50 or so kiloparsecs, the orbits of the satellites tend to be, on average, more circular. Okay, that's quantified here by this beta parameter when it becomes less than -1. So in the central regions, the orbits tend to be more circular. In the outer regions, then we tend to something that looks like more radial in terms of the structure of the orbits. So the orbits are kind of coming in and flying out, sort of in the outer regions. And so the question is, do the simulations predict this? And the answer at this stage, unfortunately, is it depends, right? It depends a little bit on like which simulation you look at, and it depends upon sort of how you cut your galaxies to what you believe to be the progenitors of these systems are. So, but this is actually an active field of research, and one thing he's going to think about to extend this is, can we reconstruct this orbital planes of satellites that are observed in the Milky Way? Okay, so all right, so that's sort of the end of the dwarf picture here. Let me just spend maybe the last 2 minutes or so talking about sort of stellar streams in the Milky Way galaxy that may have a progenitor, may not. Okay, so there was a recent analysis done and led by actually former Stanford graduate student Alex Wagner on dark energy survey, where he identified, him and his graduate student identified streams in the dark energy survey using a very complicated algorithm, right? Actually not very complicated at all. He just looked at the images, right? and saw like, and tried to figure out where the streams were. So if you can kind of like make out a few of them sitting here in this image, so these are sort of brand new structures, and the idea here is like, do these map on to sort of known, the orbits of the known dwarf galaxies, or do they even map on to, known streams that have been identified in previous surveys? And so a few of them did. A lot of them were brand new, actually. Okay, so this is just looking, basically counting overdensities of stars, just in photometric measurements here. This is interesting kind of from a fundamental physics perspective, if you will, because like understanding sort of how these streams evolve. So say if you have an object like Sagittarius, which evolves, is sort of depending upon the precise shape, and mass of the dark matter halo, the orbital structure and the wraps that it has depends upon what those properties of the halo are. So for example, there's been some sentiment that the wraps of the Sagittarius streams and the distributions of those wraps point towards a triaxial dark matter halo. Okay, so this is actually a very active field of research too, trying to understand when these objects fall in, right, understand their tidal debris that comes out, and how does that probe the host dark matter halo. In my last slide here, I'll kind of end up talking about there's another very recent piece of evidence that we might have had dark matter subhalo interactions, this time with a stream in the Milky Way galaxy. So this is the GD1 stream, which was detected in 2006 in Sloan Digital Sky Survey data. It was then characterized more precisely in the Gaia data because you can really clean up the region really well. You look at the proper motions, you look at the parallaxes, you can sort of really identify really well what objects are associated with the stream and which aren't. And the interesting point that came across in this Gaia analysis is that you kind of see, you can sort of squint and see holes there in that stream, right, in the phase space structure of that stream. And there's some idea that these holes could be associated with the impact of one of these dark matter subhalos, or even something more exotic like a primordial black hole with this stellar stream. So really now the job is kind of to theorists to understand, what's the phase space structure of these streams that we deduce generally when these types of impacts will occur, and that's something that's actively being worked on at the moment. Okay, so let me kind of end up here. Going forward. We're on the second Gaia data release now that came out early 2018. There is planned to be a third Gaia data release in 2021 or so. So hopefully we'll get more information from there. Really, I think every astronomer will tell you Gaia has basically done more than they could possibly have imagined in terms of what they've released and the science that's been extracted from it in the public. I hope I've gone a little bit towards trying to convince you that these observations can ultimately tell us something about the fundamental properties of our galaxy as well as the nature of dark matter, and perhaps inform sort of more direct searches for dark matter, such as ones that are going on here. So with that, let me close, and then if there's any questions, I'll take those.
All this fine structure experimentation now completely ruled out modified Einstein equations?
Oh, I mean, I guess there's like nothing like in what I showed that does, right?
In your opinion, is it?
There's other reasons to rule it out. I mean, I don't personally work on it, there's. I think the more interesting thing is like there's these solutions, like I was showing with the sort of the Gaia spirals. How are those created? Are those created by an impact of a dark matter blob? Are they more quote mundane sort of astrophysics like interactions with spiral arms or stuff like that? So really kind of understanding sort of the interplay between those types of scenarios. I think that's kind of the interesting directions that this data points towards. Yeah.
Could you elaborate a little on what a triaxial halo would mean in terms of the NFO?
That's a really good question. So dark matter simulation, if you just do a dark matter only simulation, which just includes gravitational collapse into dark matter halos, and Risa would know this, of course, but the halos tend to be triaxial on average if you just look at those. If you include sort of the hydrodynamical processes that come from bringing baryons in, once again, looking at the simulations and just sort of blindly saying, okay, what's the shape of my dark matter halos, they tend to be a little bit more spherical. Okay, so the question is, in the context of the standard cold dark matter model, if you believe sort of the current up-to-date numerical simulations, you might say, okay, probably something kind of spherical, but that's probably baryons. I guess maybe if you find a system that doesn't have a lot of stars associated with it, and you can measure triaxiality, that might actually tell you something. Yeah, there's scenarios done where sort of independent of baryons, you can talk about sort of what are called self-interacting dark matter models, and that tends to make halos themselves more spherical with the dark matter. But we have baryons, so we have to deal with them at this stage. So in terms of how do we map that onto the properties of dark matter, it's unfortunately, as everything else, not incredibly clear at this stage. That's a good question. Thank you.
Any questions from students?
Student, yeah. Yeah.
All right, by hand, Bob.
Yeah.
And by the time Bob's done, I want a question from a student.
Depends on what kind of student. Yeah.
Earlier you said there's no dark matter disk. How thin a disk we're talking?
Oh, well, yeah, that's the $10 million question. At the sort of thinness of our observed thin disk, scales of 100 parsecs or so. It depends upon, of course, probably the constraints depend upon exactly how thin you make it, what's the density of dark matter in that disk, so forth. But what the bound is actually on a surface mass density, sort of integrated surface mass density above and below the galactic plane. So that's what the bound is, sort of in a dark matter component in a disk. So I don't know if that helps very much, but yeah, the answer of course does depend upon sort of the structure that you assume for it. Yeah, yeah, that's right. Yeah.
They thought there was a dark.
Yeah, that's right. So if going back in the literature, I guess in the 80s and stuff, I read through this, and there was an argument about whether that disk-like structure of dark matter existed. I think that's now gone away, I guess I should say. In terms of is there a certainly there's local dark matter, right? Is it like arranged in a disk-like structure? There's no kinematic evidence of that, right? It's sort of probably something more diffuse and random and not structured in that sense.
So, keeping in mind, I don't work in this field.
Right.
Do I understand correctly that you model the dark matter as free-falling, invisible dust?
Well, I mean dust. What do you mean by dust? There's no electromagnetic interactions.
It's functionally the same thing as a functional particle.
But yeah, okay, sure. I'll give you that, I guess.
Well, look, I don't work in the field, so I'm kind of struggling to understand what equations you use. But you've made statements, theoretical statements about what this stuff does. Okay? That it's Newtonian stuff.
Sure.
So but it's in gravitational contact with the luminous, with baryonic matter all the time.
Sure.
And I've never understood how come it's so different from the baryonic matter. In other words, how come it's not gravitationally in local mechanical equilibrium with it?
I guess let me answer. I guess I'll try to answer that question as best I can. We look at like rotation curves of galaxies, right? And there appear to be more than meets the eye if the system's in equilibrium. We look at these dwarf galaxies. There appears to be more than meets the eye. And I'm sort of even putting aside the answer of the cosmic microwave background and how that actually itself really demands the presence of dark matter. Why is there a dark sector? Why is there a baryonic sector? Theoretically, I don't know. I think you might have a colloquium on that in a couple weeks, actually. But in terms of the model, I guess I agree with you. I agree with what you say. Like that's how it's modeled, but that just appears to be the way that nature is at this stage. I don't know if that's a satisfying answer or not, but okay.
One more question. John.
Student, okay.
Talked a lot about characterizing the properties of dwarf galaxies with Gaia, but is Gaia supposed to be able to detect a dwarf satellite?
Oh, that's actually kind of a good question. So can you detect, so what would be required to do that, you ask? Basically just find a blob of stars, right, that are moving kind of coherently in some direction, right? Yeah, so it actually does. So the question is like, what kind of blob can you measure with Gaia, right? So, Gaia is not incredibly photometrically precise. Dark energy survey goes like way, way deeper in terms of the numbers of stars that it measures. So, so my answer to that is probably you won't find any, dwarf galaxies as bright as the ones we know, because those would have probably been picked up already in surveys, because Gaia doesn't really push the sensitivity too low. Streams are kind of the big thing, really, to try to find, these sort of diffuse phase space structures. So those are the things that Gaia is really going to be helpful for. The question is like, how do you, is there algorithms to identify this? Yes, people are actually working on those right now, but those are not hard. I showed the dark energy survey, the very complicated, look at the images and see if something's there, right? and really at this level, right, that's kind of where we're working, right, at this stage. It'd be nice to automate this somehow, but that's what we have good young graduate students for. So.
All right, let's thank Louis again.
Yeah.